I don't want to say that Sarah's formula is a bad thing. The reason we have mathematical formulas is generally because they save us time overall. Like, for example, that whole sharing thing was fantastic because I knew there were 30 total lollipops, there were 10 total of you. And dividing by 10 is always a nice thing to do. But, for example, that's how many keys you guys had in class last time. I want to know what the average number of keys is per student in that class. Now, what I don't want to do is do the same thing that we just did. I don't want to sit up there and share. So I don't want to take my 9 keys, with JT, right? You had 9 keys. I don't want to take some of his 9 keys and give them down here to the 0. And then take some of these 8 and shake them into the 1. I mean, it works in certain physical applications. For example, Max and I were building a lizard tank. He caught a fence lizard yesterday, like that from preschool or from kindergarten. We built the tank for him, and we had to shake out to smooth out the tank's flooring. So we kind of took the tank and shook it like this, and it knocked the bedding down to a level. And that works great for a physical kind of computation. But for something like this, where you have this data in front of you, you don't want to shake and kind of share. So I want us to use Sarah's formula for sure. And as a matter of fact, it gets used so much in statistics, I want to talk about some shortcuts and some notations that we often use. So let's go over here to average. So very often, when we're drawing data that we're interested in, it's very often a sample. And we talk about the sample average, the average of that said sample. If you're talking about the sample average, we'll talk about the population average when it's important to talk about it. It's not important to talk about it right now. It gets used so much in statistics it has its own name. It's called X bar. X with a little line over its head. That's the sample average. Sample average. X bar, if you're talking about a conversation, X bar. What that is it's the sharing measure. It's the equal stake measure within the sample. So if this was our sample, it would be the equal stake measure. Now you guys, it all seems like you came into this class with an idea of how to compute the average. You add up all your data and divide by how many you have. We use that idea so much in statistics, we have notation for it. Whenever you have to add up a bunch of data in statistics, we use the Greek letter capital sigma, which means to add up a bunch of stuff, literally. They use the sigma because that's the first sound in Greek, which is the first letter in the word sum. Very often, Greek letters are used mathematically because logically they're connected. A lot of mathematics is as old as ancient Greece. So statistics is not. Statistics is only about a couple hundred years old, but they borrowed that idea of mathematical notation. So big sigma means to add up. Add up what? A bunch of numbers. We get tired of writing a bunch of numbers too. So whenever you're talking about adding up a bunch of data, you just say you're adding up the X values. X is going to be your data. That's different than X bar. And this is somewhat confusing at first to students. It's okay, you'll get the hang of it. X bar is a fixed value. The individual X's are the individual values. So the first X value for us is 0, the next X value is a 1, the next X value is another 1, the next X value is a 2. So there are 34 data values altogether we have to be adding up in this computation. And then we would divide by how many there are, and usually the letter we use in statistics is N. N for how many? For the number of data points. So summation of X divided by N. Sum X over N. Add up all your data points, divide by how many you are. Sarah, that's your formula just in symbols. And we use it so much in this class. We use it so much in all of statistics. That's why it gets symbols. I do not want this class to become a formula class. It's the last thing I want. Very often, when I talk to friends from school that said, oh my God, I survived statistics. Yeah, it's all these formulas I had to memorize. I don't want this class to be about that. As a matter of fact, there are only 2 in this entire class that you'll learn and use with any kind of regularity, and that's one of them. And we're going to use it the entire class almost. The other one is called a z-score. We'll get to him later on, like literally like 8 weeks from now. Everything else, we'll see how formulas work, and then we'll see how to use technology to get the results for us. But this one is just so prevalent and so important that it's worth learning off. Okay, check me. I'm going to try this too. Oh crap. I got to 108 and farted out. What do we got?
I've got 129.
129? We can live with that? Am I double checking it? I got to 108 and I forgot to carry something. Well, let's see, I got 108 to here, and then 24 more would be 130. That's 32 more actually. 108, 149? Is that what I heard? I'm getting 149. Did I do that wrong? Everybody check it. If you got computing machines, this is why God invented them. Go ahead. I'll swing the camera back over for those at home. Play the home game. Check my math. I'm getting 149. We got 129. I'd rather get some level of precision. 148. I was off by one. 148. There's a second over 148. I was off by one. It sounds like that's good. I can live with that. 148. We're gonna go with 148.
It was right. I missed the number.
That's okay. I did too, apparently. Actually, I put one in that wasn't there. So we've got 148. 148 in the top. 148 what? Keys. There's 148 keys amongst you all. So in other words, if you guys all came in the room, like at a party, and there was a little, like a trash can right there, it was like a decorative urn, you threw your designated driver, you threw your keys in that bin. When you all came in, all 34 of you came in and dropped your keys into that bin, there would be 148 keys in that bin. Per 34 students. Per 34 students. So now, if we wanted to spread out equally that number of 148 keys per 34 students, what would they end up being? 4 and some change?
4.45.
4.45, we'll call 4.5. How's that sound? That's about 4.5 keys per student. That's about 4.5 keys per student. 4.5 keys per student. Boom! If we spread the keys evenly, which is clever in this case because it's exactly halfway between 0 and 9. If you divide the 0 and the 9 by 2, and you're 4.5. That doesn't always happen, it just happens to come out this time because of particular reason. Notice where 4.5 is? Between this 4 and that 5 right there, yes? Between this. That means it's slightly different than the median, slightly different than the median, and maybe different than the mode. I'll talk about those in particular in a minute. But let's make sure we understand. Let's make sure we understand that calculation of what just happened and what those symbols mean. Are we okay with all three of those things? Fairly straightforward. Good. Good. So the average is the result of that computation. We're going to call it the sample average for now. We'll bring the population average in when it's important. It's not important right now. Right now, we'll treat everything like a sample. I think that makes no sense. So there's your first measure of center. The other two are fairly straightforward to calculate as well, 2 and 3. The median and the mode. The median and the mode. Does anybody remember these from previous math classes? The median and the mode. Tell me your name, my friend.
Lydia?
Lydia, which one do you remember?